Hello, welcome back to our CSCI 430 operating system. And today we'll continue our discussion about our one of another locking mechanism. So it's monitors. Okay, so this one is an alternative like software locking mechanism specification. So it may be like less like prone to creating incorrect sharing concurrency because when we talking different type like concurrency, okay, multi-thread or multi processors, okay, and only one thing, we using the example, let's say too much milk. Okay, so we will thinking if we have the atomic okay operations, how can we enter the critical sections? Okay, and of course we have already covered in the previous lecture we talked about the semaphore. Okay, so of course we giving a sample. One is like the counting one, another one is the using a 0, 1 is a binary. Okay, so basically we have the two operations. One is the wait and signal. Okay, so for the binary one, so we just like I'm switching from the 0 and 1, but for counting we will when we are wait, so we will have minus. Okay, so the number goes to negative. Okay, and then when we try to have a signal, we will +1. Okay, adding it. So there's a basic implementation. Okay, and then I will give some source code. You need to compute it and to commit the semaphore. And when we move on, how can we use the monitors? Okay, so we need to know. So is the programming language construct that provides an equivalent functionality? So to that of the semaphores, or is it easier to control? Is the idea of monitors. And when we implement in a number of programming language, including like different like Pascal, Pascal-VS or Modular 2, 3, or Java, okay. And also it has been also implemented as a program library, so we can like kind of call it as a library. Okay, we use it, and those are software modules consisting of like one or more like procedures still. Let's say if we can initializing the sequence, okay, or some like local data. So all these the monitors can provide. So what are the characteristics of monitor? Okay, so to achieve the characteristic of a monitor should have the following. So those are local data variables. They are accessible only by the monitor's procedures. Okay, so they are not using by any external procedure, only by itself. Okay, and a process enters the monitor by invoking one of its like procedures. We need to know, and then the next. So only one process may be executed in the monitor at that time. Only one, and other process that had invoke the monitor are blocked. Okay, so if you remember the different stage, right? So they are like in the block state waiting for it. So we need to waiting for the monitor to become available. Okay, so you need to remember the characteristic. So what's the synchronization right here? If we want to achieve it, so we need to use the condition variable. Okay, if you remember the table when we go through our different terms, so this one is called the condition variables for monitor. So it contains within the monitor, also accessible only within the monitor. Okay, this condition variables, they operate on like with two functions. One, C wait and C signal. Okay, but it is similar. So it's the suspend execution of the calling process on condition C. So it's called the C signal, C wait. And then for C signal, we will resume the execution of some process but after a C wait on the same condition. So right here, so we have the C wait and C signal. Okay, we have two operation, and remember when C wait suspend and then C signal, we're going to resume the execution. So you need to know. Kind of like I'm looking at the structure of a monitor. Okay, so in the monitor, we do have a list and given a condition. I see right here, C wait, right? When we calling C wait, okay, we're adding it. So in the monitor, so we maybe have some like process like goes in. We do have a local data condition variables. We talk about that. So remember, we have the condition variables and different procedures. So okay, initial like initialization code, and then when we do have some C wait, okay, so we passing C, then we pass the condition, okay, waiting after we return it back. So here's the idea of it. This one is called monitor waiting area, and giving you the problem like solution if we are using a monitor. So kind of if you look at the left side, we have the monitor, we have the buffer, and then we have integer like next in, next out. Okay, so it's a pointer, we have the count, and then give a condition, it's not full or not empty, just like helping out to keep checking. So we have a function, it's called append. Okay, appending x. Okay, so if we have the count equals to n is we define the size, right? The size equals, we have C weight. That means it's full. We are not allowed to adding anything. So it's helping us to getting like overflow. Okay. So if we pass it, then it's not full, then we're going to like adding the x. Okay, so adding the next in, and then next in equals the +1. So it's the circular. Okay, if a circle do if we try to modulate it and then count +1. Okay, keep adding it. So we will know, and then we know how many items. Okay, stored right here, and then we just say have a C signal. Okay, not empty. So we just say resume any like waiting consumes, right? So here's a um adding the append. Okay, so when we have a tag, of course we need to check, make sure it's not empty. So we check it and see weight and checking not empty. So you see why is sometimes not full and not empty right here. Okay, and then we will just like we need to like get it, right? So we need to know the out. Okay, so get the next out because it's a circular loop. Okay, so circular rate. Okay, storing it. So we're going to put in. So we need to have a modules and then total count with +1, and then just have a C signal. Okay, if that's an only way position which is not full. So once not full, one is the not empty. Okay, so that's why so you see the difference in the beginning. If you want to add something, make sure it's not full. Okay, overflow. Wednesday is the empty, so no underflow. Okay, and then just like video. So far, kind of basic, we initialize 0 for next in, next out. Okay, what's the cut? So you need to be careful if I ask you a question. I feel it was the append, what's the tick? So what's the parameter we're going to pass? Okay, not full or not empty in append, and then tick was the not empty, and then not full in the C signal. Just be careful. And kind of similar, if you remember, we have the producer and consumer, right? So also we can use the produce. Okay, we have produce function, and then we can append x, right? Adding it. So when we using the monitor this program, so we can adding it. So when we have a produce x, and then we need to add it, append it. So also this one helping us to make sure. Okay, so we only have one SS. Okay, and then we itself also have some conditional and anti. So it also can help us to doing. Okay, so how can we use the monitor? Next will be the message passing. So this one is the concept of synchronization through the message passing mechanism. We talk about that we have a mechanism like sharing the message, right? So how can we pass it? So when the process, okay, so they interact with one another's two fundamental requirements, so must to be satisfied. One is the synchronization, another one is communication. The message passing, so it's the one of the approach to provide both of these functions. Okay, so we see that how the message passing like to meet both synchronization and communication. Okay, so when they work with a distributed system or system share memories, multiprocessor, uniprocessor systems, okay, so it should be working. So when we try to do it, there's an actual function. So normally provide in the form of peer like primitive. When send function, we have destination message, receive, we have the source and the message right here, right? So when the process sends the information in the form of message to another, so destination by the destination, okay, and the process receive information by executing the receive primitive, so indicate the source and then the message. So far will be showing you like what's the synchronization including send. So we have the blocking, okay, non-blocking, and then receive, we have blocking, non-blocking, also like test for arrival. So we need to have, and then of course for the addressing, so we will talk about what's direct, send, receive, we include explicit or implicit, okay, and then for indirect, we have the static, and then dynamic or ownership, okay. And for the rest, for the format, including the context, length, fixed or variables, okay, current discipline, including like a first in, first out or priority. So all these will be like or the characteristic that we're going to design the message system for the interprocessor. So right here, okay, so you need to, when we talk about synchronization, so the communication of a message right between two processors, so implies there's some level of synchronization between the two. And the receiver cannot receive a message until it has been sent by another person. Makes sense, right? So we have to like send it out, and the receiver can receive it. So we need to specify right what happened to a process after it issue a send or receive permission. Okay, so here's a question about the synchronization. So both send and receiver, they're blocked until message is delivered. And that means like if you remember we talked about the block right here, so you need to recall kind of like remember receiver block and non-blocking, okay? And sometimes we refer as windows, okay? So it allows for the time synchronization between the process, okay? And for non-blocking send and also blocking receive, although okay, the sender may continue on and then the receive is blocked until request message arrive. Also, it allows a process to send one or more message to a variety of destination as like quickly as possible. So we can just send it, and the process might receive a message before it can do useful work. So we're waiting for the message. Okay. And next we will like doing kind of like called the non-blocking send, and then we have a non-blocking receive. So neither party is required to wait. They don't have to wait for anything. So if you see the one condition, we will block the receive. And this time we are not blocking any of it. Okay, non-blocking send, non-blocking receive. Okay. And also the addressing. And addressing is the schemes. Okay, so it used for specific like specifying the process like sent and also receive permitted. So fall into two categories. So was that one is called direct addressing, and the direct addressing, we're going to send the permitted include a specific identifier of the destination process. Also, the receive like permitted can be handled in one of these two ways we talk about it. So we need to like either require the process explicitly destination sending process. Okay, so this one is more effective. So it can allow us to like doing the cooperation okay between the concurrent process. And another one is the implicit addressing. So we need to provide the source parameters. So of the receive primitive process. So there should be a value returned. And when the receive operation has been performed, then we need to tell. So you just need to have an idea keep extending when we have talking addressing, then of course we have the direct addressing, and then for the direct addressing, we including the one is the explicitly, okay, and the ones are implicit. Okay, so we have two. And for the indirect addressing, so because those messages they are not sent directly from the sender to receiver, so there's the indirect. So when we send to shared data structure, so consisting of a queue, okay, maybe just like thinking we have a mailbox, just the idea of a mailbox, okay? Because you're thinking messaging actually is between the communication between process where we're talking. So that kind of like message, okay, sharing, okay, all this. Just like we have coming domain, but we have mailbox, we sending share consists in a queue. And for the indirect process of communication, just thinking that we have the S1 sanitary, so we have saying to a mailbox, okay, one-to-one. If we have many, okay, so we have many other processes, we send to one port, okay, and then when we receive it, or the one-to-many, okay, so maybe there's a one sender, okay, through the mailbox, we can deliver to like so many other receiver, or of course, the most case will be this one, many to many, like we have different source senders, and then send to the mailbox. Mailbox will deliver to all these like receiver. Okay, so we have multiple. So all this will be the indirect process communication. We go to a mailbox. It's a middleman. Okay, and in the general message format, of course, we will like including the header and then the body. Okay, the body should be the your message content, and in the header we should include the message type. What's the destination ID, source ID, what's your message length. Okay, they're including some control information so that we can just like we pack together as a message. It's a format we're sending out. And when we apply in the mutual exclusion, if you remember, we talk about mutual exclusion. Let's say, just like saying we have multiple process N, right? So when we have P and then we have a message, the define message, MSG right here, message. So when it's true, so we have a receive. Okay, we're going to receive. So we have a box, and then what's the message? We're going to receive, and then we execute certain critical sections. Okay, so maybe if you're going to send a certain message, what's the box, and then we have a message sending out. Okay, so we will create a mailbox in the main right here. So we have mailbox is called box. Okay, so maybe we'll send it let's say in the beginning when the box is null. Okay, then we will create all these a box. Okay, so in the middle we can receive it. Let's say let me check there's a message coming in, or like I can send certain message the mailbox to somebody with the others. So here's like we can do the indirect or direct messaging. Okay, so sometimes we can do like explicit in our implicit message. So either way is fine. And more details like examples you can see right here. Let's say we have the capacity with the buffering and what's the message. In the beginning, we have the producer and consumer. If you remember the case we are using for producer and consumer, we can use it. We can create like the message. Okay, so we can create the message while true. So maybe we have the receive for the producer. Okay, so may produce right here. So we have the producer message. Okay, we're going to say, and then we equals the produce. Okay, send, and then maybe we'll after we send it, then we can like send it out. Okay, to the consumers right here. And then how about the consumer? Okay, consumer message. Of course, we're going to receive it. So when we try to receive it, okay, right here, and then you receive it with your own message, and then of course we execute the consume. Okay, with your own message, and then we send it out and just say no. So here's the differences between the producer and then the consumer. Okay, so the difference between structure, even we do have a receive function and send function, the parameter we're going to pass will be not the same. Okay, just I need to know, and then we just create two different mailbox. Okay, one's for the producer, one's for the consumer. Okay, just create right here and just make it in case the mailbox is empty. Next is called the readers and writer problem. So this is a pretty common design problem we present in the synchronization issue. Okay, we have the readers and writers. So when we talk about this problem, we need to know in the data area they are sharing among many processes, right? So when they're sharing, some processes only read the data area. That means we have eight readers, and then some of the only like write to the data area we have writers. Okay, so this is a following condition we must be satisfied. Okay, when we design this like reader and writers problem. So any number of readers may simultaneously read the file. Okay, so there's also only one writer at a time may write to the file. So it also makes sense, like correct, if we allow two writers writing to the same area. So because conflict, right? Okay, so for the concurrency, so all this, so we only allow one writer to do that. So if a writer is writing to file, no reader may read it. Okay, because you're overwriting it. Also, if you remember to talk about the atomic operation, okay, so if we're waiting to it, we're not allowed to read it. So here's a third condition we should able to satisfy. And also for the readers, okay, we also comes with the priority. Okay, so how can we solve it? Like this. Okay, for the readers, okay, we can use the semaphore. Okay, and then we have the white sem. Okay, so right here, so we have two functions. One is for reader, one is for writer. Okay, so kind of right here, and then we'll giving a write a read can. Okay, so for the writer, right here, just like because we only allow for one way writer to write away and not allow others. So just pretty easy. Okay, so only one be a same weight. Okay, so using this the writer semaphore one. Okay, right here. So we have same way minus, and then we can the white unit. So right here, this function is the critical section. So we don't care like how it actually like creating. So we say we have a function, and then we after finish we will release it. So it's the same signal. Okay, so it's the for the that's it for one writer. So we try to grabbing. Okay, only one writer. But how about reader? So we have the while loop for true and then start, and then we have the semaphore x1. So we'll wait. Okay, so if we can able to get it, then we have the we can. Okay, so if we can equals to 1, okay, we will like same wait. So if somebody reading, because we need to fulfill the condition, right? But if we have somebody that like writing file, no reader can read it, okay, and any number of reader can simultaneously read the file. So we try to stopping the writer. So that's why, right? And then we try to send this sentinel right here to the X. That will just make sure, okay, this one is the X. And then for the same way, so we can execute the read unit, okay? So and then we have the same rate X. And then after we finish, right here we have weekend. So in the weekend you go to zero, then the same signal like of the writers like semaphore, like we'll be adding it, okay, then later we will doing the same signal X. So you see the beginning we have the X right here for semaphore, for the X right here we can plus one and make sure no writer can write because we are writing it, okay, and then the same signal, okay, we did it after we checking, okay, reading we can, okay, and then when we section then we can read it. So here's the idea, because the reader has higher priority, okay, so we put it on this part. So mainly is that if we're going to read it, a writer cannot write it, okay, so here's the high priority of the reader. Then how about in another way, if let's say the writer have higher priority, then if we put it in this way, then it's more a little bit complicated. And if you look at the writer, okay, so we have the same way. Right, this time we have the reader semaphore. Okay, so we have the x, y, z. So they're all like set default value with 1, 1, 1, 1, and then we have the writer semaphore, and then the right reader semaphore 1. Okay, so it's more like it's more complicated. Okay, it looks like the structure, like when we have a same z, and then we assemble the reader semaphore, and then we will like set the same way x, okay, and then we will set the recount, okay, and then we set the same way for the writer. Kind of pretty similar, but this time because the same way x, like this one is getting it, but this time we need to make sure, okay, we have the z, and then also the readers right between all the readers, okay, and then right now will be the x, okay, really getting the semaphore, okay. So using X, and then after we can, then we'll stop the waiter. Okay, so make sure the waiter is writing it, and we can start to read it, right? Okay, but for the waiter, if it has a high priority, so this time we have the one. Okay, so one is the more like I'm showing for the waiter, and then when we have wait, and then we have the waiting time plus one. So if we have the wait count, okay, is to one, and then we will make the with the semaphore like to wait. Okay, and when done, then we can do it like the same signal y. Okay, so if we're getting the weight, okay, if we have the same weight, okay, and then for the waiter, make sure no others waiter waiting it, then I can start to by unit. Okay, after finish, and then same signal, I can release the waiter. Okay, and right here I will doing the same weight again, and then waiter minus. Okay, just make sure um this time okay, if I'm normally writing it, then I will release the reader. Okay, and I will adding the signal y. So you see that y is mainly for the reader. That means I try to get it. So that's why you see it's so redundant. I can say redundant, but you say really similar, okay, structure, but we try to give it higher priority for the writer when you put in like which priority. Okay, so we bring like z, and then we try to add in one more external one. So we try to wait it first. Okay, hold on, and then before we release it, and then if you grant order, that means that we after the writer release anything, then we can enter. Okay, so let the reader to enter it. So once the reader entered, then we can sending the semaphore wait. Okay, to make sure no waiter can wait it, and then you can start to get a signal to make sure all the only one reader can read it. Okay, after you read it, then you can release it. Okay, so just make sure. So here's the whole design of the um, reader and writer problem, and depends on you which one you want to have a high priority, giving a priority to with it. And so far for showing different stage of the process in the queue, so either like let's say if meters only in the system, maybe we set the and W same, okay, the set, okay, that means that no Q, and the waiter only in the system, then will be like set the W same, and also the R same reset, and then YQ on the waiter same right here. Okay, so if both like the readers and waiter, the read first. Okay, so we need to set the W same by the reader. Okay, the waiter set the R same. Okay, so all the waiter Q on the W and only one reader on the sim and other readers like Q and Z. Okay, so that's why we see the C. Okay, and also we have the readers and writer, but this time writer, okay, go first if we need to write first. So kind of similar for the um but because we want to let the writer have a more right? So we will letting the writer to control the write sim, okay, and then also the out sim, okay, by the writers too. So here's the differences because for the write, if we want to let the reader go first, we let the reader control the double sim, but um we will letting the writer have a high priority, then we let it control the double sim. So you know, and then of course we will put the writer on the double sim. Okay, so semaphore, and then there's a one with the Q on the out sim, and then other with this Q and Z. Okay, so it's a kind of really similar, but just like depends on who is controlling the double sim. Okay, so if you're letting the writer go first, of course writer can control the double sim, and then the reader, then we go first, we can control the double sim. So here's the more like computer solution, and so far, we will go cover all the lecture part of our like including the mutual exclusion, semaphores, okay, monitor, okay, mutual exclusion. Um, this how can we manage the process? Okay, how can they communicate like using the process? Okay, so far for all the contents, we cover this part, and the questions, okay, some questions I just like randomly cover all these topics. Okay, you are birthday study about just like prepare. Okay, so just check the D2L, make sure you when the quiz comes out, okay, okay, some text comes out. Okay, so just be careful of the deadline. Normally I will let it open, okay, for a week. Okay, so you can finish them, and also you will see all these so the assignment, okay, or the post, just like remember finish assignment on time too. Okay, hope you enjoy the break. Thank you.